Welcome to today's session. In this video, we will explore problem number 1372, longest zigzag path in a binary tree. This is an exciting problem that challenges your understanding of binary trees, depth-first search, and dynamic programming. Let's dive in and solve it together. In this problem, you are given the root of a binary tree, and your goal is to find the longest zigzag path within it. A zigzag path is defined as a sequence of nodes where the direction alternates between left and right as you move from one node to the next. For example, if you move to the right child of a node, the next step in the path must involve moving to the left child of the following node, and so on. The length of this path is simply the number of edges it contains. Your task is to determine the maximum length of such a zigzag path in the tree. The input for this problem will be the binary tree represented by its root node, and the output will be a single integer indicating the length of the longest zigzag path. Now, let's look at an example to understand this better. Consider a binary tree where the root node is 1, with children 2 and 3. Node 2 has a right child, 4, and node 3 has a right child, 5. Continuing further, node 4 has 2 children, 6 and 7, while node 5 has a right child, 8. The longest zigzag path in this tree is formed by the sequence 1 to 3, then to 5, and finally to 8. This path alternates directions. From 1 to 3 is a right move, from 3 to 5 is a left move, and from 5 to 8 is a right move again, creating a valid zigzag path. The total length of this path is 3 edges, which is the output. In another example, consider a binary tree that is essentially a straight line with nodes 1, 2, and 3, all connected as left children. In this case, the longest zigzag path starts at node 1, goes to node 2, and then to node 3. The direction alternates from left to right as we move along the path, resulting in a zigzag length of 2 edges. This demonstrates that even in linear trees, a valid zigzag path can exist as long as the directions alternate. Finally, let's consider the simplest case, a tree with only one node. Since there are no edges in this tree, it is impossible to form a zigzag path. Therefore, the length of the longest zigzag path is 0. To summarize, the problem comes with constraints such as the tree having up to 10,000 nodes, each with unique values. Additional edge cases include understanding that single-node trees always result in a length of 0, straight-line trees produce a length of maximum depth -1, and balanced trees can have multiple zigzag paths of the same length, requiring the algorithm to identify the longest one accurately. To tackle the problem of finding the longest zigzag path in a binary tree, a brute force approach could be considered. Here, the idea is to use depth-first search, or DFS, with backtracking to explore all possible zigzag paths. The intuition behind this is fairly straightforward. For any given node, we alternate between moving to the left child and then the right child, or vice versa, while keeping track of the direction and the length of the current path. Using recursion, we can explore all possible paths. Whenever the direction alternates, we simply extend the length of the path. However, if the direction does not alternate, we restart the path from the current node. While this approach might seem viable for smaller trees, its inefficiency becomes apparent with larger datasets. This is because the algorithm essentially recalculates the zigzag paths for the same nodes multiple times, leading to a time complexity of n squared. As a result, the brute force approach suffers from redundant calculations, making it impractical for large trees. A more efficient solution is the optimized approach using DFS with state tracking. The key here is to avoid recalculating paths repeatedly by maintaining state information during the traversal. Specifically, for each node, we keep track of 2 states, the longest zigzag path starting with a left move and the longest zigzag path starting with a right move. By propagating the current state down to the children during the DFS traversal, we can compute the maximum zigzag path length without restarting the calculation from each node. The recursive helper function calculates the path lengths for both directions and updates a global maximum as it progresses. This reduces the time complexity to n, as each node is visited exactly once, and the work done at each node is constant. Additionally, this approach is highly efficient for large trees since it eliminates redundant computations. While a similar result could be achieved with dynamic programming on a tree, that method requires extra space to store the states at each node, which the optimized DFS avoids. After evaluating the different approaches, the optimized DFS with state tracking was chosen because it strikes the right balance between efficiency and simplicity. The brute force method, while easier to implement, was deemed unsuitable due to its poor performance on large inputs. On the other hand, dynamic programming on a tree, though effective, introduces additional memory overhead and complexity that the optimized DFS avoids. One of the key insights that led to this decision was recognizing that the problem could be solved by maintaining two states at each node, the longest zigzag path starting from a left move and the longest starting from a right move. This allowed us to avoid redundant calculations and compute the result in a single traversal. While the optimized DFS requires careful implementation to manage the recursion states, it is significantly more efficient, running in O(n) time while requiring minimal additional memory. This makes it the most practical and scalable solution for this problem. In this problem, we are tasked with finding the longest zigzag path in a binary tree. A zigzag path is defined as a sequence of nodes where the direction alternates at each step, for example, moving left to right, then back to left, and so on. To solve this, we use a depth-first search, or DFS, approach combined with backtracking. The key idea is to traverse the tree recursively while keeping track of two important variables: the direction of the previous step and the current length of the zigzag path. These variables help us explore and validate potential paths as we navigate the tree. The ultimate goal is to determine the maximum length of any valid zigzag path in the tree, starting from any node. This sets up the foundation for our algorithm. To implement the algorithm, we first initialize a global variable max_length, which will store the longest zigzag path we encounter during the traversal. Next, the core of the implementation lies in the recursive DFS function. For each node, we handle three main tasks. First, we check if the node is null, which serves as our base case to terminate recursion. Second, we update max_length by comparing the current path length with the maximum found so far. Finally, we make recursive calls to explore the left and right children. If the current direction is left, we continue the zigzag path by moving to the right child and incrementing the length. Simultaneously, we also reset the path length when moving to the left child. Similarly, if the current direction is right, we move to the left child to extend the zigzag, and reset the path when moving to the right child. This ensures that we explore all possible paths while maintaining the zigzag property. Edge cases, such as single-node trees or trees with only left or right subtrees, are also accounted for in this design. The algorithm relies on several key insights that make it both intuitive and efficient. First, the recursive DFS approach ensures that we explore every possible path in the tree. Second, the problem exhibits optimal substructure, meaning the zigzag path length for a node depends only on its immediate children, which makes recursion a natural choice. Third, the alternation between left and right at each step is the defining aspect of a valid zigzag path, and our algorithm explicitly enforces this. To achieve this, we use a combination of data structures, including the binary tree itself, integer variables to track the current path length and direction, and a global variable max_length to store the result. From a complexity perspective, the algorithm is efficient. The time complexity is O(n), where n is the number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. The pseudocode for the DFS traversal makes these ideas concrete. The helper function DFS takes three parameters: the current node, the direction of the previous step, and the length of the ongoing zigzag path. If the current node is null, the function simply returns. Otherwise, it updates the global max_length variable with the maximum of its current value and the ongoing path length. Depending on the direction, the function recursively explores the appropriate child nodes. If the direction is left, it continues the zigzag by moving to the right child and increments the path length. Simultaneously, it resets the path length when moving to the left child. The process is mirrored when the direction is right, alternating between left and right children. The driver function longest zigzag initializes max_length to 0 and starts the DFS from both the left and right children of the route, ensuring that all potential zigzag paths are considered. The algorithm concludes by returning the maximum path length found. To illustrate the algorithm, consider this example tree. Starting from the root node, we explore both the left and right subtrees. For the path 1246, the directions alternate is left-right-left, resulting in a zigzag length of 3. Similarly, for the path 1357, the directions alternate is right left right, also yielding a zigzag length of 3. The maximum zigzag length across all paths in this tree is therefore 3. This example highlights the importance of alternating directions and resetting the path length appropriately to maintain the zigzag property. The DFS traversal ensures that all possible paths are explored, and the use of a global max_length variable allows the algorithm to efficiently track the longest path. This approach, with its linear time complexity and minimal space usage, provides an effective solution to the problem. Here, we define the longest zigzag function inside the solution class, which will calculate the length of the longest zigzag path in a binary tree. First, we initialize a class variable self.max_length to 0. This will keep track of the maximum zigzag path length we encounter during the traversal. Next, we define a helper function DFS, which stands for depth-first search, to traverse the tree recursively. This function takes 3 parameters: the current node, a boolean is_left that indicates whether the current path direction is left or right, and length, which keeps track of the current zigzag path length. Inside the DFS function, we first check if the current node is null. If it is, we simply return since there's nothing to process. Otherwise, we update self.max_length to the maximum of its current value and the current path length. This ensures we always store the longest path found so far. Next, we handle the zigzag logic. If the current direction is left, we continue the path by calling DFS on the right child with is_left set to false and increment the length by 1. At the same time, we restart a new zigzag path by calling DFS on the left child with is_left set to true and resetting the length to 1. Similarly, if the direction is right, we continue the path by calling DFS on the left child and restart the path by calling DFS on the right child. Finally, we start the DFS from the root node, exploring both left and right directions with an initial path length of 0. At the end of the function, we return the value of self.max_length, which holds the length of the longest zigzag path we found in the tree. This value is the result of all the recursive calculations and updates performed during the DFS traversal. By the time we reach this point, the function will have explored every possible zigzag path in the tree, ensuring that the maximum length is correctly determined. This concise and efficient implementation leverages recursion to navigate the tree and maintain the zigzag pattern while updating the maximum length dynamically. Here, we begin the Java implementation for finding the longest zigzag path in a binary tree. The class starts with a private variable, maxLength, to keep track of the longest zigzag path found during the traversal. The main method, longestZigzag, takes the root of the binary tree as input. We initialize maxLength to 0, and then perform depth-first search twice, first starting with a left turn and then with a right turn. This ensures we explore all possible zigzag paths originating from the root. The DFS method is the core of our solution. It takes 3 parameters: the current node, a Boolean flag indicating the direction of the current path, and the current length of the zigzag path. If the node is null, we simply return since there's no further traversal possible. Otherwise, we update maxLength by comparing it to the current path length. Depending on the direction, we either continue the path in the opposite direction or restart the path from the current node in the same direction. This recursive strategy ensures we evaluate all potential paths in the tree. The implementation also includes the treeNode class, which defines the structure of a binary tree node. Each node has an integer value and references to its left and right child nodes. There are 3 constructors provided: a default constructor, one that initializes only the node's value, and another that initializes the value along with the left and right child nodes. This flexibility allows us to construct trees of varying structures easily. With this setup, the treeNode class serves as the foundation for traversing and evaluating the binary tree in the DFS method. Together, the solution class and treeNode class provide a complete framework for solving the longest zigzag path problem in a binary tree. Let's begin with a simple example to understand the process. The tree consists of 3 nodes arranged in a zigzag pattern. Starting at the root node, 1, we call the DFS function twice, once assuming we are going left and once assuming we are going right. For DFS 1, true, 0, we update the maximum length to 0, as no path has been established yet. Then, we move to the right child, node 2, while increasing the path length by 1. At the same time, we attempt to move left, but since there's no left child, that branch terminates immediately. At node 2, we continue the zigzag path by moving to the left child, node 3, increasing the path length to 2. This updates the maximum length to 2. At node 3, there are no children, so this branch ends. The recursive calls ensure that all possible zigzag paths originating from node 1 are explored, updating the maximum length along the way. After completing the exploration starting with the assumption of a leftward path, we return to the root and repeat a similar process, this time assuming the path starts rightward with DFS, 1, false, 0. However, this symmetrical exploration does not yield any longer paths. Thus, the longest zigzag path remains 2. Moving to a larger example, this binary tree features more nodes and a more complex structure. The goal remains the same, to calculate the longest zigzag path by recursively exploring both leftward and rightward paths from the root and maintaining the maximum length. With this setup, we'll work through the tree step by step to determine the result. For this larger tree, we begin from the root node, 1, calling DFS in both directions. When we move left to node 2, we update the maximum length to 1, as this is the first step in a potential zigzag path. From node 2, we move right to node 4, extending the path and updating the maximum length to 2. Since node 4 has no children, this branch ends. Next, we explore the right subtree of the root. At node 3, we update the maximum length to 2, matching the longest path found so far. Moving left to node 5, the path extends, but the maximum length remains 2. From node 5, we go further left to node 6, increasing the path length to 3. Node 6 has no children, so the recursion concludes. With all paths explored, the longest zigzag path in this tree is determined to be 3. Finally, let's examine a straight-line tree, where each node only has a single right child. Starting at the root, node 1, we call DFS in both directions, but since there's no left child, the leftward path terminates immediately. Moving right to node 2, the zigzag length is updated to 1, but subsequent calls restart the path at each node due to the lack of alternating children. This process continues for nodes 3 and 4, with no further increases to the maximum length. Since no zigzag paths can be formed in a straight-line tree, the longest zigzag path remains 1. To analyze the time complexity of our solution, let's start by understanding the operations involved. The algorithm employs a depth-first search traversal, which systematically visits each node in the binary tree. Since every node is visited exactly once, the total number of recursive calls is directly proportional to the number of nodes, denoted as n. For each node, the algorithm performs a constant amount of work, such as updating the maximum zigzag length and initiating up to 2 recursive calls. These operations take constant time, or O1. As a result, the overall time complexity is determined by the total number of nodes visited, which gives us O(n). Now let's look at the space complexity. The primary factor affecting space usage is the memory required for the recursive call stack during the depth-first search traversal. The depth of this call stack is determined by the height of the binary tree. In the best-case scenario, for a perfectly balanced tree, the height is O log n. However, in the worst case of a completely skewed tree, where the tree resembles a linked list, the height becomes O(n). Aside from the call stack, the algorithm uses only a few fixed variables, such as self.max_length and the parameters passed to the recursive function, which require constant space, or O(1). Therefore, the overall space complexity is O(h), where h represents the height of the tree. Let's break this down further by analyzing the best, average, and worst cases. In the best case of a perfectly balanced tree with n nodes, the height is O log n, resulting in a space complexity of O log n for the call stack, while the time complexity remains O(n). For an average binary tree, the height is typically proportional to O log n as well, so the space complexity is still O log n, with a time complexity of O(n). In the worst case, a completely skewed tree has a height of O(n), leading to a space complexity of O(n). However, the time complexity remains O(n) across all cases, as every node is still visited exactly once. To further highlight the efficiency of our solution, let's compare it to a naive approach. A brute force method might involve recalculating the zigzag path for every node, which would require re-examining all possible paths in the tree multiple times. This approach would result in a time complexity of O(n) squared in the worst case, as it redundantly traverses subtrees. The space complexity, however, would still depend on the height of the tree, or O(h). In contrast, our optimized approach eliminates these redundant calculations by ensuring each node is visited only once during the depth-first search traversal. This allows us to achieve a linear time complexity of O(n), while maintaining the same space complexity of O(h), making it significantly more efficient. Finally, let's formalize the mathematical proof of these complexities. For time complexity, the depth-first search traversal guarantees that each of the n nodes is visited exactly once. Each visit involves a constant number of operations, so the total time complexity is O(n) ** O(1), which simplifies to O(n). For space complexity, the maximum depth of the call stack corresponds to the height of the tree, h. Since additional memory usage is limited to a few constant space variables, the total space complexity becomes O(h). In summary, this optimized solution achieves the best possible time complexity of O(n) and a space complexity of O(h), making it both time efficient and memory efficient. Now, let's discuss some common mistakes to watch out for when solving the longest zigzag path problem. One frequent error is not resetting the zigzag counter properly. For example, if you're switching from a left-to-right path to a right-to-left path, failing to reset the counter can cause the path length to accumulate incorrectly, leading to wrong results. The solution here is straightforward: always reset the path length whenever the direction changes. Another mistake is performing inefficient traversal. A brute force DFS without optimization, like pruning or memoization, can result in redundant calculations, especially in large or deeply nested trees. To address this, you can use dynamic programming or caching techniques to store results and avoid unnecessary recomputation. Lastly, incorrect edge handling can be a problem. For instance, forgetting to check if a node is null before accessing its children can lead to runtime errors. To prevent this, always validate that a node exists before attempting further traversal. Additionally, ignoring constraints is another pitfall. Constraints like distinct node values, tree height limits, or input size are critical to consider, and overlooking them can cause your solution to fail edge cases or exceed time limits. It's essential to carefully read the problem statement and test your code against edge cases, such as the smallest or largest possible trees, as well as highly unbalanced trees. Another common issue is misinterpreting the problem statement. For example, misunderstanding what qualifies as a zigzag path, such as assuming it must include all nodes in a horizontal or vertical sequence, can lead to incorrect implementations. The fix here is to clarify the problem's requirements and examples before jumping into coding. A careful initial understanding can save you a lot of debugging later on. From an interview perspective, this problem highlights several key patterns. It typically involves tree traversal techniques like DFS or BFS, and alternating between states, such as switching directions during traversal. Recognizing this alternating pattern early can help you structure your approach effectively. Using recursion or iterative stacks to manage state transitions is essential, and memoization can significantly optimize performance by reducing redundant computations. For example, you can store results for subtrees to avoid recalculating their values multiple times. However, there are trade-offs to consider. While brute force solutions are straightforward to implement, they become inefficient for larger trees. Optimized solutions, such as those leveraging dynamic programming, are faster but more complex to implement. Similarly, recursive solutions are easier to write but may encounter stack overflow issues with very deep trees, while iterative approaches avoid this but require careful state management. In interviews, it's crucial to clearly communicate your thought process. Start by outlining a basic brute force approach to demonstrate comprehension, then explain how you plan to optimize it, emphasizing how you handle edge cases and improve performance. There are also related problems that share similar concepts and can help deepen your understanding of tree-based questions. For instance, LeetCode 1372, longest zigzag path in a binary tree, directly aligns with the current problem. LeetCode 124, binary tree maximum path sum, focuses on calculating paths within a tree structure as well, but with a different metric. LeetCode 543, diameter of binary tree, is another classic problem involving the traversal and computation of maximum paths. Finally, LeetCode 98, validate binary search tree, emphasizes managing state during traversal to ensure correctness. By practicing these problems, you can strengthen your skills in tree traversal, path calculations, and state management, which are common in this category of questions. There are several alternative approaches to solving the longest zigzag path problem, each with its own pros and cons. One option is to use DFS with backtracking. This approach is simple to implement and explores all possible paths, but it can be inefficient for large trees due to its high time complexity. A more optimized option is dynamic programming combined with DFS. This method uses memoization to reduce redundant computations, making it ideal for larger inputs. However, it's more complex to implement and debug, as managing the memoization structure adds overhead. Finally, iterative BFS is another approach. It avoids stack overflow issues that can arise with recursion, making it suitable for balanced trees. However, it requires careful queue management and additional space to track the state of each node. Understanding these approaches allows you to choose the best one based on the problem constraints and input size. Great work on completing this problem. To summarize, we used a DFS with backtracking approach to find the longest zigzag path in a binary tree. Depth-first search and recursion played a key role in solving this. Remember, mastering these concepts will help you tackle similar challenges with confidence. If you enjoyed this session, don't forget to like and subscribe for more. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!